Can a choice you make, right now, in this very moment, decide what happened 5 minutes ago? Sounds like nonsense, doesn't it? It violates the most fundamental rule of our existence. Cause comes before effect. You can't unspill the milk. The past is the past. It's written in stone, a fixed and unchangeable country we can only look back on. But what if it isn't? What if there's one experiment, the most baffling, counterintuitive, and furiously argued over experiment in the entire history of science, that seems to tear up that rulebook? An experiment that shows the future reaching its ghostly hand back in time, and gently editing the past. Tonight on the Science Audit, we are putting this cosmic outlaw on trial. We are not just going to talk about it, we are going to build it from the ground up, piece by piece. We're diving headfirst into the notorious quantum eraser, tracing every single photon, stress testing every bizarre explanation, and answering the one question that seems to break our brains: does the future actually control the past? Okay, before we start meddling with the space-time continuum, we need to get our footing. We have to start with the grand gateway into all of quantum weirdness, the experiment that first shattered our classical, common-sense view of the world, the double-slit experiment. You might have heard of it, but let's really build the intuition here, because everything hinges on understanding this one strange fact about reality. First, let's imagine a scenario that makes perfect sense. You're at a shooting range. In front of you is a solid barrier with two thin, vertical slits cut into it. Behind that barrier is a target wall. You take a high-powered paintball gun and you just let loose, spraying paintballs at the barrier. What do you expect to see on the target wall behind it? It's obvious, right? You'll get two distinct vertical stripes of paint, each one corresponding to a slit that a paintball managed to pass through. Some might ricochet, but the ones that make it through act like tiny, solid bullets. Particles behave like particles. Predictable, solid, real. That's the world we live in. Now, let's shrink this down. Way down. To the fundamental constituents of reality itself. We replace our paintball gun with a device that can fire single particles of light, photons, one at a time. This is key. We're not sending a wave of light, we're sending individual, indivisible bullets of light, one after the other. So, what do we expect to see on the detector screen after we've fired a million of these photons? Common sense screams we should see the same thing as the paintballs, two distinct lines. But that is not what happens. Not even close. Instead, what slowly builds up on the screen, one tiny dot of light at a time, is a series of many lines, a barcode of alternating bright and dark bands. This is called an interference pattern. And here's the mind breaker: interference is something only waves do. Think of ripples on a quiet pond. If you drop two pebbles and at the same time, two sets of circular ripples expand outwards. Where the crest of one wave meets the crest of another, they combine to make a bigger wave. That's a bright band. Where the crest of one meets the trough of another, they cancel each other out, leaving the water flat. That's a dark band. That beautiful pattern of highs and lows is exactly what we see with single photons. This leaves us with a conclusion so absurd it feels wrong. A single photon, a supposedly indivisible particle, leaves the gun, and then somehow travels through both slits at the same time as a wave of pure possibility. This single wave then interferes with itself, and only then does it decide where to hit the screen as a single particle. It's as if it explores all possible paths and then its final location is determined by the sum of all those possibilities. I know. It doesn't make sense in our macroscopic world. Just stay with me. It gets much, much weirder. Now for the twist that has baffled physicists for a century. What if we get curious? What if we try to catch the photon in the act? We decide we're going to find out, once and for all, which slit it actually goes through. So we place a tiny, sophisticated detector right next to one of the slits. It's designed to give a little click whenever the photon passes by, without destroying the photon itself. We're just going to peek. The moment we do that, the instant we gain what physicists call witch path information, the entire game changes. The interference pattern completely vanishes. Poof. Gone. And what are we left with? Two simple, boring lines. Exactly like our paintballs. The very act of observing, of acquiring information about its path, forces the photon's wave of possibilities to collapse into a single, concrete, particle-like reality. It's as if the universe has a strict rule: I can show you my mysterious, holistic wave nature, or I can show you my definite, localized particle nature, but I will never, ever show you both at the same time. You, the experimenter, get to choose which face of reality you want to see. Your question determines the answer. So, the rule seems to be, no peeking. If you know the path, you get a particle. If you don't know the path, you get a wave. This seems weird, but manageable. Until the brilliant, mischievous physicist John Wheeler came along in the late 1970s and asked a truly profound question. What if you could cheat? What if you waited to make your choice? Waited until after the photon had already passed the slits and was well on its way to the final screen? What if you could choose, at the very last picosecond, whether to place a detector in its path to see which way it came from, or to just let it go and reveal its wave nature? This was his genius thought experiment, the delayed choice experiment. And when it was finally performed, the results were staggering. It works. A choice you make after the photon has supposedly committed to being a particle, or a wave seems to reach back in time and determine what it was in the past. But we can push this idea even further into the realm of the unbelievable. We can raise the stakes. We can not only choose to look, but we can choose to erase what we saw. Enter the delayed choice quantum eraser. To build this beast, we need to introduce one more piece of quantum magic: entanglement. Now, entanglement has a reputation for being spooky action at a distance. Let's demystify it. A better way to think of it is as a perfect, unbreakable correlation. It's not telepathy, it's a shared history. In our lab, we start by firing a high-energy laser into a special type of crystal, usually a beta barium borate crystal. Through a process called spontaneous parametric downconversion, a single, high-energy photon enters the crystal and is split into a pair of lower-energy twins. For the rest of their existence, no matter how far apart they travel, these two photons will be part of the same quantum state. Let's call them the signal photon and the either photon. Their entanglement is like a perfectly choreographed dance. Imagine two dancers who are given a single, secret rulebook at birth. The rulebook says, if dancer A performs a clockwise spin, dancer B must instantly perform a counterclockwise spin. They go to opposite ends of the universe. When you watch dancer A and see them spin clockwise, you don't need to send a message to dancer B to know what they're doing. You know instantly that they are spinning counterclockwise, because their actions were correlated from the very beginning. You didn't cause dancer B's spin. You simply revealed a pre-existing, perfect correlation. That's entanglement. Now, we use these entangled twins to build our eraser experiment. The setup is intricate, so let's walk the photons through it, step by step. The signal photon, our star performer, is sent on the direct route. It heads straight towards the double-slit apparatus, just like in our first experiment, and then continues on to a final detector screen, which we'll call detector 0, or D0. This is where we will look for our interference pattern. The idler photon, its twin, our informant, is sent on a much longer, more convoluted journey. It doesn't go near the slits. Instead, its path is a carefully constructed maze of beam splitters and mirrors. A beam splitter is like a half-silvered mirror. It's a quantum coin toss. It has a 50% chance of letting a photon pass straight through and a 50% chance of reflecting it at a 90-degree angle. This is our tool for creating ambiguity. The idler's maze is designed to do one of two things with brutal efficiency. Some paths in this maze will lead to a pair of detectors. Let's call them D3 and D4. If the idler photon hits D3, it tells us with 100% certainty that its signal twin went through slit A. If it hits D4, it tells us its twin went through slit B. These detectors preserve the which path information. Think of this like putting a tiny, unerasable red or blue tag on the photon's history. But, and here is the genius of the experiment, other paths in the maze lead to a final beam splitter. This beam splitter recombines the paths in such a way that when the photon leaves it and hits one of the final detectors, D1 or D2, it becomes fundamentally impossible, even in principle, to ever know whether it originally came from the slit A path or the slit B path. This is what we call erasing the which path information. It's not like deleting a file on your computer. It's more like taking two secret messages written in invisible ink, laying them on top of each other, and then burning the paper. The information is irretrievably scrambled. Now, here is the timeline. This is the part that twists your brain into a pretzel. Because the either photon's path is so much longer, its fate, whether its path information is preserved at D3, D4 or erased at D1, D2, is decided nanoseconds after its signal twin has already arrived, died, and made its mark on the final screen, D0. So, let's run the experiment. The room is dark. The detectors are on. We fire millions and millions of entangled pairs through the apparatus. We stand and watch the main screen, D0, where the signal photons are landing. What do we see? Absolutely nothing interesting. A blurry, washed-out splotch of light. A smooth hill of hits, as random and meaningless as static on a TV screen. There is no interference pattern. No stripes. No hint of wave behavior. It looks like a complete failure. But we've been collecting data on the other side of the lab. Our informant, the idler photon, has a story to tell. For every single dot that appeared on D0, We have a time-stamped record of which detector its idler twin ended up at. This is called coincidence counting. It's like a cosmic bookkeeping system, allowing us to perfectly match up every pair of twins. Now comes the moment of truth. We go to our computer, and we start to filter the data. First, we tell it, of all the millions of dots on screen D0, please show me only the ones whose idler twin happened to hit detector D1, one of our erasing detectors. The computer processes the request. The random blob of dots on the screen thins out, and from the chaos, order emerges. A perfect interference pattern. The barcode of light and dark stripes snaps into view. The very photons whose path information we chose to erase in the future behaved like waves in the past. My God! Let's try the next one. Computer, now show me only the dots whose twins hit the other erasing detector, D2. Again, an interference pattern appears. But this one is shifted. It's an anti-interference pattern. Where the first pattern had a bright stripe, this one has a dark stripe, and vice versa. It's the perfect negative image. Okay, so what about the others? Computer, show us the dots whose twins landed on detector D3, the one that told us the path was slit A. No stripes. Just a single clump of hits on the screen, exactly what you'd expect from a particle. And D4, the one that told us the path was slit B? Again, another clump. A particle-like pattern. Let's stop. Take a breath. And let the sheer insanity of this sink in. A measurement choice we made over here on the idler photon, a choice to erase or preserve information, now, seemed to dictate whether its twin signal photon behaved like a spreading wave or a localized particle over there, back in the past. And here's the most elegant part of the trick. If you just take all those separate patterns we just filtered, the interference from D1, the anti-interference from D2, the particle clump from D3, and the particle clump from D4, and you just add them all back together on the screen, what do you get? You get that same boring, random, featureless splat we started with. The patterns perfectly cancel each other out, like adding a sound wave to its exact inverse to get silence. This feels like it shatters the foundation of reality. This is the evidence that fuels the claims of retrocausality. But hold on. There is a crucial, non-negotiable rule that saves reality from descending into time travel paradoxes. It is called the no-signaling principle. And it's a fortress. What it means is this: look only at the main D0 screen by itself. Without having the data from the idler detectors, without being able to sort the dots into subgroups, the pattern you see is always random. Always. You, the observer at screen D0, can never, ever tell what choice your friend across the lab is making at the idler detectors. Your friend can't use their choice of measurement to send you a secret Morse code message into the past. All you will ever see is statistical noise until you get that phone call, traveling at, or below, the speed of light, telling you how to sort your data to reveal the hidden patterns. So relax. You can't send tomorrow's winning lottery numbers to your past self. But the profound mystery remains. The correlation is real. The future measurement and the past event are inextricably linked. How on earth do we explain this? This is where physics turns into philosophy, and the world's greatest minds split into warring camps. So let's audit the models. Let's imagine we're detectives who have just witnessed this impossible event, and we have 4 brilliant, but very different, lead suspects for what's really going on. Suspect number 1, the Copenhagen interpretation. This is the classic, the old guard of quantum mechanics, formulated by pioneers like Niels Bohr and Werner Heisenberg. In our detective analogy, the Copenhagen view says, there was no definitive event in the past until you completed your investigation. The photon's journey wasn't wave-like or particle-like. It was an undefined cloud of potentialities. The crime scene of the past simply does not exist as a settled story until the entire measurement context is known, and that includes the future measurement of the idler photon. The measurement over at the idler detector doesn't change the past. It is the final piece of information needed to write the past for the very first time. The past isn't a fixed photograph. It's a story that is only told once all the characters have played their part. Suspect number 2, the many worlds interpretation. This is the sci-fi favorite, first proposed by Hugh Everett III. It's both elegant and extravagant. The many worlds detective says, there was no single crime scene. Every possible outcome happened, but in separate, parallel realities. When the signal photon went through the slits, the universe itself split. In one universe, it went through the left slit. In another, the right. Later, when you make your erasing or path-preserving measurement on the idler photon, you are not altering any past. You are simply discovering which branch of the multiverse you, the observer, happen to be on. There's a branch where you erase the information, and in that entire universe's history, the records consistently show wave-like behavior. In another parallel branch, you chose to keep the path information, and in that universe's complete history, the records show particle-like behavior. All the stories are self-consistent within their own timelines. There is no paradox, just an infinite library of universes where every possibility is made real. Suspect number 3, the retrocausal interpretation. This is the bold radical who takes the evidence at face value. Physicists like Yakir Aharonov and the proponents of the two-state vector formalism are the chief advocates here. The retrocausal detective says, folks, maybe the future does influence the past. Just not in the way you think. They ask us to reconsider the nature of time itself. Instead of seeing the universe as a series of dominoes falling over in a line, what if we see it as a story constrained by both its beginning and its end? Let's go back to our crossword puzzle analogy. You have a clue for one across, and a clue for one down. They intersect. The answer for one heavily restricts the possible answers for the other. Which one causes the other? Neither. The correct, final solution is the one that is globally consistent with all the clues, from every direction. Retrocausal models propose that reality works this way. The state of the photon at the beginning, its preparation, provides the cross clues. The measurement we make on it at the end provides the down clues. The only actual histories that are allowed to exist, the only events that we see, are the ones that satisfy both sets of constraints simultaneously. It is a handshake across time. No messages are sent, no laws are broken, but influence is a two-way street. Suspect number 4, Superdeterminism. This is the ultimate conspiracy theorist. This is the interpretation that looks at our entire detective story and declares, the whole thing was a setup. Superdeterminism, an idea seriously considered by giants like Gerard T. Hooft, gets rid of the paradox by attacking the most fundamental assumption of all science, that an experimenter is free to choose what to measure. This view proposes that the state of the particles being created and the choice you, the scientist, are about to make in your brain, are not independent events. They were both determined by a shared set of conditions in their deep, deep past, a common cause, perhaps going all the way back to the Big Bang. It's like a magician who tells you to freely pick a card, any card. You think you have a choice, but he expertly forced a specific card on you. The outcome seems miraculous, but only because you were unaware that your free choice was correlated with the state of the deck from the start. In the superdeterministic universe, there is no paradox because there was never any freedom. Your choice to erase was destined from the beginning of time, and so was the particle's corresponding wave-like behavior. It solves the puzzle, but the philosophical cost is staggering, the illusion of free will. So, after interrogating all our suspects, what is the final verdict from the science audit? Does the future touch the past? The answer, like quantum mechanics itself, is a superposition of a profound yes and an emphatic no. And no, the future does not rewrite the past in any meaningful, science fiction way. You cannot send information backwards. Causality, the engine of our everyday experience, remains undefeated. The thermodynamic arrow of time, the reason coffee cools and eggs don't unscramble, still points resolutely forward. Our story still seems to be written in one direction. But yes, the quantum eraser forces us to abandon a simple, linear, billiard ball view of cause and effect. It demonstrates, in the starkest terms possible, that what we call an event in the past is not a solid, independent object we can put under a microscope. It is a story we construct. And that story is only complete, only coherent, when we possess information from both its beginning and its end. The future measurement doesn't tear out yesterday's page, it provides the final sentence that gives the entire paragraph its meaning. Reality, it seems, isn't a chain of causes. It might be a vast, self-consistent web, a tapestry woven simultaneously from the threads of the past and the threads of the future, where every part must align with every other part for the grand picture to hold together. Here's a final thought experiment for you to take with you, away from the lab and into your life. Think about your day so far. Right now, as you recall it, it might feel like a jumble of disconnected moments, a random conversation with a barista, a passing thought you had while driving, an unexpected email lighting up your screen. It's a blurry, featureless splotch of data, just like the initial hits on our detector screen. But tonight, or tomorrow, you might make a significant decision. You might commit to a new career path, or decide to end a relationship, or dedicate yourself to a new creative project. Now, look back on today with that future decision as your context. You begin to filter the data. That random conversation with the barista wasn't random. They said something that planted a seed. That passing thought wasn't an accident. It was the first whisper of the new idea. That email wasn't a distraction. It was the catalyst that forced your hand. Suddenly, you can see a pattern, a line, an interference fringe in the noise of your life. So, did your future choice magically change your past? Or did it just give you the lens you needed to finally reveal the coherent thread that was always there, woven into the tapestry, waiting for the right question to be asked? The audit of reality never truly ends. For every answer we find, a dozen deeper, stranger questions emerge. So, I invite you to continue the journey. Click the video on your screen right now for another deep dive, another audit of the fundamental rules of our universe that will stretch your mind even further. And before you go, I need your verdict in the comments. Be the detective. Which of these 4 mind-bending interpretations, Copenhagen, many worlds, retrocausality, or the rigged game of superdeterminism, do you find the most compelling, or maybe the most unsettling? There is no wrong answer, only a fascinating debate to be had. And finally, if you believe that wrestling with these immense questions is one of the most vital and exciting things we can do as human beings, then do yourself a favor. Hit that subscribe button, ring the bell, and officially join the audit. We do this every day. Let's figure it out together.